Hello and welcome to the course Internet of Things. I am Neda, and in this course I am with you to teach you the IoT. The agenda that we have for this whole course consists of 8 lectures, and these 8 lectures are the first lecture is Introduction to the Internet of Things and microcontrollers and electronic devices, OSI model layers and protocols like IP, TCP, UDP, HTTP, CoAP, MQTT. MicroPython programming on Raspberry Pi Pico. We learn how to program MicroPython, and Lecture 5 is about messaging protocol like MQTT, CoAP, and also data format like JSON and buffer protocol. And lecture 6 is about connectivity with Wi-Fi, and lecture 7 is long-range connectivity with LoRaWAN. And lecture 8 is sending sensor data to IoT platforms and dashboards. The learning targets are in this course is that you understand very well the IoT systems and their fundamental concept. That includes how we gather data, how we transport this data, and how visualize this data that they are coming from the sensors measurements, as well as how we can integrate this data gathering, transportation, visualization with a third-party system or services. Also, we are going to learn how to develop the software part of an end-to-end IoT system based on IoT platforms. Today, I'm going to talk about Internet of Things, and this lecture includes subtopics like Introduction to IoT, IoT Reference Model, Entities of an IoT System, IoT Roadmap, and Pilotcases of IoT Lab. Okay, what is Internet of Things? What is the goal? First of all, we should learn the IoT architecture to reach our goal, which is the Internet of Things. Our goal is that we can control a set of electric or mechanical devices via the internet. Or these devices can be controlled by interaction with each other and can collaborate with each other. But how? The IoT architecture consists of different parts. As you can see in this photo, the objects that we call them things that can have that they can be like washing machine, TV, lamp, microwaves, or etc. These things can be objects that we have at home or industry, or the things that are installed on the city level. These objects should be controlled by the internet. But these things cannot connect simply to the internet by themselves. So we need the tools and devices that we can send messages via them to these objects using the internet. So these objects can do the task that we as a user demand. For example, they can turn on and off a lamp, or a microwave can heat food or do many other tasks. We need to command these objects or things because they don't know the language of the internet. We need something that we can push our mobile or tablet button that they send command can interpret or translate our command or talk for these objects. Our translator, interpreter, converter, this is all these words used together interchangeably. This translator, interpreter, and converter is microcontroller. This converter or microcontroller from one side is connected to the internet and from the other side is connected to our things or objects. Today we use lots of different converter chips used in the industry. So companies produce module chips that connect to the internet and our objects. In the next slide, I will show you this kind of modules and how many types we have and they are using. In this lecture, the converter interpreter chip that we are going to learn is called Raspberry Pi Pico W or Pico. So overall, if I want to say that IoT in a simple words is interaction of everyday objects and devices through the internet, and that enabling them to collect, share, and respond to data and making our lives more convenient, efficient, and smarter. Okay, what is IoT reference model? As I mentioned here, this is the IoT reference model and is a conceptual framework that provides a common understanding of the various components of an IoT system. An IoT reference model is a guide or framework that helps in understanding and building IoT system. It consists of different layers, and each layer is responsible for a specific function, such as collecting data from sensors, processing it, and transmitting it over the internet. By following this model, developers can create IoT solutions more easily and ensure that various components work together seamlessly. So in one end, we have device. It's connected to local gateway, and through local gateway, we are connected to the cloud as a backend. And from the backend, we can get insights about data that is sent there. And the user here has interaction, physical interaction with device, and visual interaction with the device, with the app. IoT reference model has 5 layers. The most top layer is called application layer. This layer is where the end user interacts with the IoT system. This layer includes the application and services that run on top of the IoT platform and provide a user-friendly interface. The fourth layer is called platform layer. This layer is where the data processing and analytics occur. This layer is responsible for managing data that is collected from sensors and devices and providing analytics to enable decision making. Let's say we can do machine learning analytics and make inferences about about the data and make decision. The third layer is called connectivity layer, and it includes the communication protocols and technologies that enable devices to communicate with each other and with the platform. The second layer is middleware layer, and this layer provides a bridge between the platform layer and the device layer and enables communication and data exchange between them. The first layer is called device layer, or we can call it physical layer, and this layer includes the physical devices and sensors that collect and transmit data to the platform. We will go through all these layers later in the next lecture. So let's see what is the drivers of IoT. What I mean by drivers, I mean why we come to the IoT, what is the advantages, why we should use IoT. Okay, the drivers of IoT play an essential role in shaping the rapid growth and adoption of the IoT technology across different sectors. The first reason is that a small, inexpensive, and low-power computers. These miniature and low-cost computers like microcontrollers and single-board computers have become powerful tools that enables IoT development. These devices have sufficient processing capabilities and consume minimal power, which makes them perfect for creating scalable, connected IoT solutions. And examples that we can have here is like Arduino, uh, ESP32, ESP8266, and Raspberry Pi Pico as a microcontrollers, and also we have Raspberry Pi as a single board computer. The second reason is a small, inexpensive, low power sensors. IoT relies heavily on real-time data collection, which is powered by various types of sensors. These sensors are becoming more affordable and energy efficient, which allows developers to deploy IoT networks easily and cost effectively. Examples of such sensors are temperature, humidity, motion sensors, and many more. I will show you all types of sensors that there are in different shapes and different models. The third reason is short and long range connectivity. A variety of connectivity options exist for IoT devices to communicate with each other and centralized systems. These options can be categorized into short range connectivity, such as Wi-Fi, Zigbee, and Bluetooth, low energy, that we call it BLE, and long range connectivity that includes LoRaWAN, NB-IoT, and LTE-M. These varied connection options offer flexibility and adaptability for IoT devices to function effectively in different scenarios. The fourth reason is cloud computing and storage. IoT devices often generate large amounts of data that need to be stored, processed, and analyzed. Cloud computing and storage providers offer massive resources to manage this data effectively and allow developers to access these services on a model that is called pay per use or pay as you use model. So in this case, you can benefit this cloud computing and storage. And the leading cloud providers include Amazon Web Service, AWS, or Google Cloud Platform, GCP, and Microsoft Azure. This enables a more efficient sharing and processing of resources, making it easier for IoT systems to expand and scale. The fifth reason is standard IoT protocols. IoT protocols are sets of rules and guidelines that define communication, data transmission, and processing for connected devices. Standards protocols ensure that different IoT devices manufactured by different vendors can work together seamlessly. This interoperability is critical to continued growth of the IoT ecosystem. Examples of key IoT protocols include MQTT and QoAP. So when you are going to develop an IoT application, there are always this question they come up that what development board, what microcontroller or what single board computer I should choose, which kind of sensors I should choose, or which communication, what is the data storage, and what IoT protocols I should follow, and what about the battery or power consumption, and many others, many other question that you should consider as a IoT application developer. Okay, IoT high-level use cases. IoT enables these core use cases in different sectors. Efficiency, for example, trash bins that let you know they are full, or convenience, for example, remotely preheating a holiday home. For example, before you go for a holiday and you, let's say you have a house in somewhere in the mountain, and you wanna make it warm before you go and arrive there. So you can easily use sensors and remotely control them, or turn it on to be warm. The place, and when you arrive there, the place is already warm, and that is a kind of convenience features of the IoT. And also, you can get new insights. For example, a crowdsourced air quality map. A crowdsourced air quality maps involves gathering air quality data from multiple sources, primarily contributed by individuals or communities, and using low-cost air quality sensors. These sensors are installed at various locations where concerned citizens or businesses want to monitor air quality. The gathered data is then processed, combined, and mapped in real time, resulting in an air quality map that can be accessed by anyone. Using the power of the crowd, air quality maps provide a more comprehensive and granular view of air quality at a localized level. There are other also sectors that include connected consumer products, citizen sensing, industrial IoT, and many more. For example, connected consumer products span a broad range of industries and include a smart home, like internal connected appliances such as a smart thermostat, a smart lighting system, connected security cameras, and home automation system that provide better energy efficiency and security and convenience. Or wearables, smartwatches, fitness tracker, and health monitoring devices that collect accurate health data and help users maintain a healthy lifestyle, and integrate seamlessly with smartphones for notification and connectivity. Also, entertainment, smart TVs, and connected streaming devices that offer personalized content recommendation and integrate with other internet services and access app ecosystem. Also, it can be connected vehicles that car with integrated connectivity features such as telematics, and telematic system gather data including vehicle location, driver behavior, engine diagnosis, and vehicle activity, and visualize this data on software platforms that help fleet operators manage their resources. Or it can be remote vehicle control or infotainment system. And also over the air software update, and also advanced driver assistance systems. Also, it can be smart appliances, large and small home appliances like refrigerators, washing machines, and coffee makers that can be controlled via a smartphone and offer remote diagnostics, automatically reorder consumable, and optimize energy usage. So you can see that IoT use cases is very broad and wide. The entities in an IoT system. Entities, we have many different entity in IoT system that makes the whole IoT a system of IoT. So we have devices, we have sensors, we have gateways, we have backend, and we have clients. I will explain one by one each of these entities, and we will see what is their role and what does they mean. What do they mean? Okay, device is an embedded computer with sensors and actuators. As you can see in this photo, if we open up this device, we can see that there's a microcontroller that we call it in short MCU with constrained resources. Also, the chip can have connectivity, built-in connectivity, or it can have external module. Also, there is a slow processor and with a limited memory and low power usage inside this device. And they are often battery powered or even harvesting energy. This is the device. So, what is sensors? Sensor is a device that detects and measures changes in its environment, such as temperature, pressure, lights, or motion, and converts these changes, these analog signals, into electrical signals. So these temperature, pressure, and light, motion are all analog signals or physical properties that, using these sensors, they become electrical signals, and it can be used in the system. So examples are temperature, sound, light, distance, and motion. And you can see here some photos of them. I brought some examples of sensors, and they are, for example, here we have LHT 65 LoRaWAN temperature and humidity sensor. You can see all the features and the application that this kind of sensors can be used. For example, it has a LoRaWAN class A protocol, and I will explain what is LoRaWAN protocol later and about LoRa technology. But, just to show you that what is the different kind of sensors that we have, I brought them here. And applications that this sensor measures temperature and humidity for you. And the application that you can use this sensor in is wireless alarm and security system, home and building automation, automated meter reading, and industrial monitoring and control, and long-range irrigation system, and many, many others. Let's see the other sensor. We have wireless infrared object detector sensors, and it works with the data rate at 868 megahertz to 915 megahertz. Also, it has its property, and it's like that. It detects the object by using infrared. The other one is LoRaWAN temperature and humidity sensor. This is another type that designed for in-home and in-building usage for consumer or facility management applications. As it is mentioned here, you can use it up to 100 meters away from a LoRaWAN gateway and up to 1 kilometer from a gateway with an outdoor antenna. The other sensors that is manufactured by Sensitive company in Lund. It is a water leak sensor stripe. And this sensor combines water leak detection, open close, temperature, and light sensor in one smart device. We have also temperature and humidity sensor in another type that it can measure indoor ambient parameters. I mean the humidity and temperature. And I'm not sure where is the by pack wireless technology and co is designed. Another sensor that we have is LoRaWAN ultrasonic based distance detection sensor. And as you can see, this sensor measures the distance by the ultrasonic, measuring the sound difference between object and it. And a flat object. Another sensor is parking lot sensor. If you install this sensor on the ground, it can detect if there is a car here or no, because it can sense it if there is some object close to it or no. So we are using this kind of sensor in a parking lot. The other type is wireless temperature, humidity, air pressure, and motion sensors. You can see all these parameters, I mean temperature, humidity, air pressure, and motion, are combined in one sensor, and you can have this sensor for measuring these parameters all in one. Another type of sensor is standalone environmental sensors that it's measure the air quality, and this is manufactured by Seed Studio. We have another type of LoRaWAN water leak detector, and and this is designed to monitor and detect water leaks in real time using the LoRaWAN communication protocol. The device is typically used in residential and commercial buildings, industrial environments, data centers, or any location where water leaks may occur and causing damage or operational disruption. This sensor is equipped with a sensitive moisture sensor that detects the presence of water or moisture. Upon detection, it sends an alert via the LoRaWAN network to a gateway, which then forwards the alert to a central monitoring system. This real-time notification allows for early intervention and can help minimize the damage caused by water leaks. Another sensor is LoRaWAN passage counter byte that gives insights about how a building is utilized by keeping track of people flow and occupancy using the people counter with the LoRaWAN wireless communication protocol. No camera or personal data is used, meaning you will not have issues regarding the European GDPR. Okay, let's see another entities in the IoT system. What is actuator? An actuator is IoT. In IoT is a device that performs physical actions or movements in response to external signals or commands, typically from a control system or a sensor data. Actuators help IoT system interact with the physical world by converting electrical or digital signals into actions, analog signals, like opening or closing a valve, moving a motor, or turning a switch. For example, there are different types of light, movement, sound, heat, and current. You can see in this photo, there is servo motor, LED that we will use in this course, and relay and step motor. As a simple example for actuator is that, let's say we have a LED in a system. If the temperature of a room goes higher than 30 centigrade, then we want to the LED turn on. So this is kind of actuator that act based on some commands, based on some situation, it's act. Okay, another entity is gateway. Gateway connects local devices and networks to the internet. All of us, we have seen gateway and we have in our home that we connect to it. Our devices can connect to gateway and we connect to the internet. LoRaWAN gateway is one sample of this gateway. That's called TTN indoor gateway, and it can be a normal Wi-Fi gateway for Wi-Fi devices that all of us have it for sure, and it can be transparent. The gateway can be transparent. It means that it can forward data without modification, or it can be convert payloads. It will do data modification for interpreting the data. For example, if two devices in the IoT system are connected with different technology, one connected through Bluetooth and one connected through Wi-Fi, so how they are connecting with each other, how they is supposed they understand the data that they send, and this is based on the different protocol. So in this case, we need a gateway that can do data modification for being able to interpret the data for these two devices. Maybe some wants to ask question that, okay, what is difference between router and gateway and the modem also? Let's call gateway as a last door. I mean, the router to the cloud. As you can see in this photo, if we say that we have 4 rooms, room 1, room 2, room 3, and room 4, and each has its own router that we call it router 1, router 2, router 3, and router 4. They are only connected. Each room is connected, and the computer in this room are connected only with each other. But if they want to connect it to the cloud, we need a gateway here that all of them send the packet data through the gateway to the cloud, and we can connect to the cloud. But here, I want to explain you what is the difference between the modem, router, and gateway. Before, we had modem. Modem is a mashup word of modulation and demodulation. Modulation means that the analog signal comes and modulated to the digital, and demodulation means that the digital demodulates to the analog. So before we had modem that we could get internet from ISP, and this internet was provided to our computer. Since each ISP gives one address to you, so you only be able to have one device, that is in this case PC, that connected to this Ethernet cable. But what if I want to connect more than one device? I have mobile, I have tablet, I have iPad, I have PC. In this case, they introduce router. Router gets that is connected here to that Ethernet cable and gets the internet, and it provide different addresses for different devices for you. Is like that. Let's say that you have a building and your mail address box, mailbox address is in that building. When the letter come, first it come to the building and then it goes to your mail address. So it's like a broadcasting address for your devices. And here in this case, you can have many devices that is connected to the router, and router gets the internet from modem. And they come up with idea that, okay, we have modem and router. What if we have only one device that can both get internet and route and give us as you know, routing that data, give many different addresses. So they come up with the gateway device. Gateway is a combination of router and modem together. As you can see in this photo, we remove this modem and router and only we have a gateway, so we can have many devices that get many different that all of them can access to the internet. There are different Wi-Fi and LoRaWAN gateways. Wi-Fi gateway, it can be like this: LoRaWAN outdoor gateway and LoRaWAN indoor gateway. You can see there are different shape and size of the gateways. Another example of a gateway is a Pygate gateway with Europa data rate of 868 megahertz and in EU 915 megahertz frequency. And this is an 8-channel LoRaWAN gateway and connect your VP and LoP or GP and connect up any other PyCom devices for a decentralized IoT network. So as you can see in this photo, we have many different development boards and connectivity. I call development boards because development boards can be MCUs and can be SPC. MCU, I mean microcontrollers, and SPC single board computers. Here in this photo, all of them are MCUs, and this is Arduino Mega and many others, M5 Stack and Heltec, many other boards from different manufacturers. And here in the right side, we have different connectivity. For example, we can have Wi-Fi, we can have Bluetooth, we can have LoRa, LTE, and Sigfox. So different development boards and different connectivity and different sensors. We can see in IoT we have so many alternatives. Okay, let's see what is the next entity. Backend. Backend server or web service endpoint that exists in the cloud. We call cloud as a backend. This backend receive data from devices and send the devices commands. And it provides data to the client. Let's call it uplink when you send the data to the client. Also, it's very highly available, scalable, and have high bandwidth because cloud is a centralized data centers and there are lots of storage and computing capabilities there that many devices can connect to this cloud, and it is scalable and all the time should be available. And it can provide storage, data analysis, and it uses third-party software. For example, SMHOE, that is a third-party software that you can get all the weather information from there about the region that you want to know about, the temperature, humidity, the wind speed, the wind direction, every and you can get it as an API and have it, and you can do data analysis on that. So let's see what is the client, the last entity that we introduce. Client It can be a client application, for example, dashboard, or it can be third-party service client. The client can be your a mobile application, as I said, and it can read measurement data from devices via the backend or via the cloud. And you can write control data to the device via the backend, and we call it downlink. And multiple different application can share one backend. To the cloud, many different clients can connect, and they can interact with each other through that backend. So after we learn about the IoT and IoT reference model and the entities that exist in the IoT, now it's time to learn about IoT roadmap. IoT roadmap actually it shows you how to start working with a sensor and send your data to the cloud, and you can see the data from device goes to cloud and ended up there, and you can have insight about your data. So according to this photo, we start from here and we select IDE in integrated development environment and programming language. Here in this stage that we call it development environment, we have many different alternatives. VS Code, Arduino, Atom, and many others that they are the IDEs, and MicroPython, Arduino, C++, and etc. that they are programming languages. You can choose whatever you want, but in this lecture we are going to use VS Code as the IDE that we are using to develop, to write our program, and MicroPython as a programming language. After choosing this, it is the next level, that it is device and sensor configuration. In this step, we should select the microcontroller that we want and install plugins and libraries. In this level, you should choose, you should configure the board, you should choose board library, you should configure serial ports, download serial ports driver if it's needed, and you should update the firmware and many other things if it is required. And in this course, we are going to choose Pico W, and because there are many other options and you can use as MCUs, but we are going to use Pico W. So after choosing your development board or MCU, it's time to choose and connect and test sensor functionality. We have many different sensors as I show you, but in this course we are going to work with DHT11, and this is the sensor for measuring temperature and humidity, as you can see in this name, humidity and temperature. After choosing the sensor and connect it to the device, to the MCU, and test it that is work properly, the next level is a network connection, that you should choose your network protocol. In this lecture, we are going to talk about Wi-Fi connectivity and LoRaWAN connectivity. Wi-Fi for the short range connection and LoRaWAN for a long range connection. And when we are going to choose LoRaWAN connection, we have many different network server that they are based on LoRaWAN. protocol. And one of the famous one is the Things Network, or TTN, that we are going to talk about it, and the others are Helium or Chirp Stack. The next level is data visualization. Uh, Data visualization shows that you are in this step you are going to visualize your data, and we can call it cloud, where my data end up and I can have insights, and I can see what is happening, and I can monitor, let's say. And this is like a dashboard for the user. And we have different alternatives: low code IoT solutions, big data IoT solutions, and self-hosted IoT solutions. For the low code IoT solutions, we have MQTT and webhooks that in this course we are going to talk about it, about data cake. And also there are ADF root and UBDots. For big data IoT solutions, there are Google Cloud IoT, Amazon IoT, IBM IoT. And for this, if you are going to host your data visualization, that we call it self-hosted IoT solution, it comes with Ticket Stack and Node-RED. This is whole the IoT roadmap. So a possible path to follow is like this. Start here, and you have VS Code and MicroPython. We will choose it as an IDE and programming language. We will have the board, and our board is Pico, and the sensor is DHT11, and we will have Wi-Fi and MQTT and LoRa and TTN and MQTT. There are two alternatives here that we can connect our device to the cloud and see the information. And also for the visualization part, we have data cake and ADA fruit. So we will follow this path to work with and see our data. This is a demo that finally all the data ended up here in the data cake. I will teach you later how you create your account. Like I have this account here with my name here, and also they are the devices that your sensors that you have. You can see your data in your dashboard in the data cake. And for example, you can see the CO2 measurement here, and also you can see the temperature and the others. So we have some pilot cases of IoT Lab. I'm going to talk about some of them, not all of them. We have many pilot cases that we have done in IoT Lab in Kalmar. One of them is B-Lab, one of them is Kalmar Demme, Stenswark, QTF, Job Out, Event Center, PM Venner, Svenska Våg, and many others. Let's start by B-Lab. The pilot case B-Lab, if I want to tell you some background, is that the B-Lab Technology Sweden develops and manufactures products and services for digitally connected beehives, and their goal is to introduce eco-friendly communication technology to monitor the bees population and honey production. Thus providing a battery-powered wireless communication base and energy-efficient sensor system to transmit real-time hives information to beekeepers this is the goal of this B-Lab company. And Problem is that they want to increase productivity and the farmers need to provide a suitable environment for the bees. For example, the farmers must maintain temperature, humidity, and air pressure in the hives to maximize honey production. If, for example, the queen that lives in the hive feels that this is very warm inside the hive, then maybe she feel that she wants to flit from the hive, and in this case, many other bees, let's say half of them will fly away with this queen, and this is not good because the beekeepers will lose these bees that they need for sure. These bees for more honey production. So the motivation was that since these bees pollinate the majority of flowering plants that help our ecosystem and produce honey and other valuable products such as bee wax, propolis, bee pollen, flower pollen, and royal jelly, these high value products motivates farmers to collect bees and indulge full time in apiculture. In this pilot case, the IoT Lab in Kalmar proposed this approach that you can use the PyCom VP as a MCU. MCU, when I say MCU, we mean microcontroller. This is abbreviation word for that. And the sensors that we can use is the temperature, humidity, air pressure, and VOC, and also HX711 that measure the load cell, and also DS18B20 temperature. And we have communication that we use here is LTE, narrowband IoT, and QAP. And I will talk about these protocols for sure later because they are different protocol for different layer of the network that we have. And here we measure the humidity and temperature and send it via I2C protocol, digital protocol, that I will talk about it later, to the VP. VP is our MCU and it sends the data through LTE narrowband IoT to the cellular tower and through the co-app to the server, to the cloud. The next pilot case is Kalmar Demme. The purpose of establishment is that the Kalmar Demme is a wetland that was artificially created near the Kalmar airport to remove nitrogen from the water that was used to de-ice the runaways in winter. The problem that was here is that wetlands are subject to damages and destruction. For example, flooding or seawater influx. Collecting information and data to preserve and conserve the wetland for optimal decision making is essential. Thus, in Kalmar Demme, there is a requirement for different measurements, for example, water level, weather conditions, wind direction, oxygen, carbon dioxide, and water conductivity. Motivation is that the measurement at Demme used to be performed manually on site. Before we go on site in person and write what is the water level and what is the conductivity through reading from the devices. But this pilot case aims to automate data measurement and processing by implementing an IoT-based monitoring system. Pilot case Kalmar Demme, the IoT lab that proposed approach is that we installed a number of sensors at the demo that we had it, and we proposed a Helium network-based IoT communication infrastructure. And as you can see, we have different sensor here: conductivity sensor at demo, water and wind station at the demo, and we installed 10 distance sensors, and as you can see, we visualize the data and we can see the water level in this demo. And also we have conductivity sensor data that measures the conductivity, because when the sea water comes up, it can come to the wetland. In this case, the wetland water can be salty, and in this case we can measure this saltiness through the conductivity sensor data. Another pilot case is Stenswark. Stenswark is a company in Osaka that produces meat-based products. And the aim is to automatically measure temperature and humidity inside the factory. We propose LTH65. This is a sensors that measure temperature and humidity. And we also send this data through LoRaWAN to the TTN gateway. And through the TTN, we visualize the data in a data cake. And as you can see here, we have this visualization and we can monitor it. So there is no need to write every week 2 or 3 times, go and write it manually. Now we made it automate, and we can report to the authority very easily the temperature and humidity. Another pilot case is QTF, and QTF there is a QTF company is like that there is a filter tube, and they want to know when to change the filter which is connected to the filter tube. There are pressure sensors. If the pressure is high on one side, that water comes in, and the pressure is less on the other side, that water goes out, it shows that it is time to change the filter. So we used ESP32 and VP as an MCU, and the sensors that we use is a DF robot water pressure sensors and STC41 CO2 sensors, and also 44E42 Hall effect. And the communication that we use is NB IoT and Modbus TCP/IP. Modbus is a protocol. So the next pilot case is job out. The job out company wants to detect if someone is using the product, and they want to motivate people to use it because they are concerned about the health. It is called job out, which is a mesh up of workout and job. It shows that when you sit down or stand up, you are doing a workout while you are doing your job. So we used ESP32 Health Tech as an MCU, and the sensors we use is velostat and pressure sensors. And the communication that we have here is LoRaWAN. The other pilot case is event center. In event center, they want to reliably detect when someone touches this plexiglass by hand or feet. The MCU that we use is Arduino Mega, and the sensors we use is velostat and infrared. And the communication that we use here is serial communication. I have brought here the paper that we published just 2 years ago. This is called DynaSense, that is a dynamic scheduling for IoT devices sustainability. In this paper, we propose a dynamic sensing algorithm for an IoT-based waste management system. The main concern of this paper is power saving, because we connected this MCU to the bin, and the sensor that we use is the distance sensor LiDAR that we can measure how much the bin is full, and this algorithm helps to reduce the waste bin overflowing and provide better sanitation, and is also helpful in reducing the fuel cost of waste collection vehicles. So the MCU that we used in this case was PyCom LoPi4, and the sensor was LiDAR, and the communication that we use is LoRa. Connected product. A connected product is more than just a single physical device. When we say connected product, it refers to a connected ecosystem of devices, softwares, and services that work together to provide a seamless user experience. The entirety of one or more devices, gateways, backends, apps, and the services they represent. Together, these components form an integrated system that enables efficient data collection, processing, analysis, and dissemination, providing a personalized and engaging user experience. For example, a smart home system that includes a set of connected devices like thermostat, light, bulbs, security camera, a gateway device that enables the communication between devices and the cloud, a mobile app that allows the user to control and monitor devices remotely, and backend services that store user data, perform complex analytics, and provide insight into device usage patterns. So you can see we have device, we have sensors, we have gateways, we have backend, and we have client. All entities in all system. It consists the IoT system. It consists all of these entities, and they form together an IoT system. Okay, hands-on. I would like to tell you about one of the system, that how it works, and I would like to ask you that pick one of these connected products IoT project and draw a reference model of how it works. For example, here you have a camera that is connected to your door of your home, and we call it door cam. And this camera, and the door is locked, and camera is installed to the door. Okay, so this camera take a photo, and if your neighbor or any other person is coming and close to it, it being filmed and shows that he is stepping in your neighbor. And the owner, that is you, and you install this camera to your door, you're checking camera, and you see that okay, if it is based on the entry log that you get from the system, that shows that okay, there is someone that is coming, and you can see from the services that you are getting from the IoT server, then you can decide that okay, the door should be open, for example, and then you open the door, and or the door should not be open and you keep it locked. So you can see how it works. In this slide, I brought some products, and you can follow these links. For example, Philips Hue and Safecast, or the others, and you can search about it, and you can see how they work, and they are called connected products. That overall you can see how IoT reference model is and how they work. So we define IoT and understood the drivers behind it. In this lecture, we look at the drivers of IoT, We got to know the entities in an IoT system. The entities are devices, MCUs, sensors, gateways, backend, and clients. Now we know a simple reference model for IoT system. We have seen IoT Roadmap and the software and tools. And also we have seen some IoT projects done at IoT Lab in Kalmar. The next lecture will be about microcontrollers, sensors, and actuator or overall electronic devices that exist in the IoT system. Thanks for your time, and if you have any question or feedback, please Slack me, or you are very welcome to IoT Lab in Kalmar or in my office.